Okay, so let's start. This meeting is recorded as usually. So hello everyone. Welcome to episode 41 of Warsaw Quantum Computing Group meetings. And today our guest, our great speaker is Victoria Goliber from D-Wave. So Victoria is joining us from Germany, and she will give a talk titled Building Hybrid Applications with D-Wave. Before we start, we would like to thank our strategic partners, Narto and Cogit, for supporting us, as well as thank our honorary partners for helping us in advertising this event. Yeah, I think we can start. So Victoria, if you are ready, I will now stop sharing my slides, and the Zoom is yours, so you can start.
All right, so you should all be able to see my slides now, yeah?
Yes, I can see it. Maybe just one announcement to participants. So as usual, if you have any questions, please post your questions on our chat during the lecture, and I will try to read the most important and most urgent questions during the lecture, but there will be also the Q&A session at the end. And as usually, this meeting is recorded.
Great.
Okay, we can start.
Thank you. Well, first of all, thanks for having us here again. I think this is our third time now giving a guest lecture here. So the first two times, the first time we came and we spoke about just, D-Wave in general and different customer use cases and application areas that we're seeing a lot of interest in, and a lot of publications and webinars and things like that you can look at. And then I believe the second session, I gave a more technical talk where we looked at how you can formulate problems as the quadratic model, which is required for our products. And we looked at some simple examples, just formulating a problem as a binary quadratic model and running it on the D-Wave quantum computer. So as kind of the next step in this series, I thought that this time we could talk about building hybrid applications. So D-Wave not only offers quantum computers, but we also offer hybrid solvers, which leverage both quantum and classical compute resources. So we'll talk a little bit about that and look at a very simple example, and then we'll look at a larger scale example, which will run live on our hybrid solvers. So if you have interest in the other areas, the webinars previously were recorded, so you can go back and look at any of those, but you can also just dive right in with hybrid applications. There's not really a need to start with the quantum computer directly, which is really nice. So you can kind of use whatever seems like it's the most useful, the most relevant for you and your needs. So I'm Victoria Goliber. I'm a senior technical analyst on the European team for D-Wave. I am based in Germany, despite my accent. So yeah, I'm here in Germany. I'm on, the same time zone. So I'm around if you have any questions. Here's my email address. You can connect with me on LinkedIn, anything like that. But I've been with D-Wave for a little over 4 years now, and I've been in this role that whole time, really teaching new users how to use our tools as they've developed over those 4 years, helping customers and potential users see some of, what they could do with our products if you put those into your workspace. So let's just dive right in. And we really have one intro slide that's kind of all of D-Wave here, because as I mentioned, we've covered this in the past. So I really wanted to dive in. But at D-Wave, we have quantum computers, which I think is what most people know us for. And so our most state-of-the-art system that we have online now is our Advantage system, which is over 5,000 qubits. Since our previous system, we increased connectivity, which allows you to embed larger problems, more complex problems directly onto the quantum computer chip and run larger problems for your needs. We also have other systems available online that have different, advanced technology available, so you can go and play around and see what's there. Feel free to try out anything. And to access our solvers, both our quantum computers and our hybrid solvers, we have our Leap Cloud platform. And this is where anyone can go and sign up for a free account. You can sign up, you can get free access to our solvers, to our documentation, to code examples. We have an in-browser IDE, which I'll show with my demo a little bit later. But basically, there's just tons of information and resources here on our Leap Cloud platform for anyone getting started. So you can go sign up for free, you can get free access time. If you link your GitHub account so that we can see all the great things that you're developing with that free access, it'll actually renew every month. So you can have, ongoing free access to our platforms. So you can really, build out some of those use cases and try it out and get a feel for what it can do. So let's dive into our hybrid solvers. So as I mentioned, we have a portfolio of hybrid solvers available. So I'm going to talk most of today about our constrained quadratic model hybrid solver. This is really our latest and greatest hybrid solver. It was released in October last year, so it's still relatively new. So you may not see it a ton in the literature yet because everyone's still, trying it out and seeing how the performance is. But based on our own internal benchmarking, we've been seeing really, really good performance with this constrained quadratic model hybrid solver. So a few key things here. So for anyone that's brand new and getting started, this solver is going to make it way easier to formulate your problems and write up your software code to actually run your problems on a solver. So what this allows you to do is to come up with like an objective function. So basically like a cost function that you're trying to minimize. Our solvers are really good at minimization problems. And so you're going to come up with this cost function, your objective function that you want to minimize, and you can encode that exactly as you would write it down as a math formula on a piece of paper. You don't need to worry about, these biases and things that we've talked about in the past. It's a much simpler representation of your problem. And then you can also have your constraints like choose exactly 2, or each person in this set gets exactly 1 assignment, or constraints like that, like equalities and inequalities. You can now write those just exactly how you would as a math expression on a piece of paper, rather than figuring out how to combine all of these into one model, which is what we showed in the last seminar that I gave. So it allows for a more native representation of your problem. It's really easy to get started with this new solver because you don't have to do any of this like manipulation to get one equation that represents all aspects of your problem. You can kind of hand each piece over separately, and our software tools will do all of that combination for you. So some of the more technical details here I have listed. So previously with our hybrid solvers, we allowed you to use our BQM solver, which is binary quadratic model. So each of your variables would have to be binary. We then, a little bit later, introduced our discrete quadratic model, which allowed you to have variables that could choose a value from a discrete finite set. So for example, if you're coloring a map, you could say each state gets to be either red, yellow, green, or blue. That's an example of a discrete variable that you could do on our discrete quadratic model solver. Now with our constrained quadratic model solver, you've got binary, you've got a way to work with discrete variables as well. And we've also added in integer variables. So this is like a huge leap ahead that really, really helps with building up a model that makes sense to you rather than having to convert everything to binary variables. So it allows for a lot more flexibility. We also all of our models require linear and quadratic terms only. So you'll see with all of these acronyms, BQM, DQM, CQM, they all end in QM. That's the quadratic model. So all of your objectives and constraints need to be represented as quadratic equations. So higher order terms, there's ways to work around those, but essentially you will be working down to a quadratic model. Our problem solver, this hybrid solver, can handle problems with up to 500,000 variables, both integer and binary. And you can have up to 100,000 constraints. And as I mentioned, these constraints could be equalities or inequalities, all sorts of different formats there. So that's like a very quick overview. I know there's a lot of information and a lot of details there, but for those of you that have tried out our previous solvers, this bar graph here is a really, really interesting one that I hope gets you really excited to try out this solver. So first of all, if you look at this, we have, kind of 2 sets of bars on this graph, one for QBOs and one for constrained models. So QBO, if you recall, stands for quadratic unconstrained binary optimization. You are handing over one equation that you're looking to minimize. Now you can take constraints and kind of encode them into that equation, but it requires you to do some like weighting of penalty coefficients and things like that that can take a lot of parameter tuning. So generally when we talk about unconstrained problems, it's something where you're just trying to like minimize the cost functions and you don't have a separate set of constraints. So in that domain, our binary quadratic model hybrid solver performs really, really well. In these unconstrained problems where you just have an objective and no constraints that need to be satisfied for a feasible solution, our BQM hybrid solver is still going to be the best that you have available to you. That can run up to 1 million binary variables. It's a very, very powerful solver. However, if you have a problem that does have constraints, so you do have differentiators between feasible and infeasible solutions, we're seeing really, really good performance from our constrained quadratic model hybrid solver. So this set of bars on the right, this constrained models, you're going to see your performance shoot way up by using this constrained quadratic model, primarily because we're going to handle all of that like weighting and penalty coefficients, those Lagrange parameters. If you've done some of our programming before, that weighting is all taken care of for you. Your solutions that are returned, it's going to tell you if they're feasible and infeasible. So it does some of that post-processing for you as well. And so it's just a really, really powerful solver for these constrained problems. So let's dive in a little bit more on some of the details. So as I mentioned, you can use binary and integer variables, and we also have ways to set up discrete variables built in as well. So it encompasses all of those previous solver variable types. It has easy equality and inequality constraint handling. You can just write down, x1 plus x2 equals 5 and send that over in your software, and it just makes it really, really easy. It handles linear and quadratic terms in both the objectives and constraints. And we've also introduced what we call symbolic math. So you can literally write in your software code x1 plus x2 equals 5. And because of how you create these variables symbolically, the software knows exactly what to do with that. So it's just so easy to get started. I really like to, now that we have this, I actually really like to dive in with this one first when I'm teaching a training course, because it's just so easy and intuitive to work with. So again, some of the statistics, I mentioned these already. You can have up to 500,000 binary and or integer variables. You can have up to 100,000 constraints. For those of you that have a little bit more familiarity with our binary quadratic models, you might be familiar with the term biases. That's kind of how many of those linear and quadratic terms are there overall. This can handle 750 million of those biases. So these are some really large problems. These are really starting to approach like real world scale, industry sized problems. And so we're really excited to see what people can do with this. So hopefully after today, you'll be excited to go and try it as well. Dig into some of our code examples. We have a bunch using this solver. And so I'm primarily going to go over 2 different code examples. One is a simpler one, and one is a more complex demo that you'll be able to play with after I'm gone. It's in Leap. You can try it out for yourself. So let's just dive right in with our first example. So the knapsack problem, this is a problem that some of you may have heard of before. So basically think about it like you've got an empty backpack, a knapsack, and you want to fill it with items that have the highest value. You want your backpack to be the most valuable backpack you can make from a set of objects that you have. However, your backpack has a weight limit, right? It's got a capacity that you can't exceed. If you try to put too much in there, it's not going to fit, it's going to break. So you really have to meet that capacity limit. You cannot exceed it. So this is a problem that comes up a lot in the real world in different variations and things like packing shipping containers, right? So you've got like a hard-sided shipping container. You can only fit so many boxes in there, and then it's full. There's nothing that you can add to it. It's full. And you want to make as much money as you can. So you want to pack in that shipping container the most valuable items. So when you maybe sell them at the destination, you're going to make the most profit. So this is a really useful problem that comes up in a lot of different variations in the real world. And so it's a nice one to start with. And it's an optimization problem that we can define pretty simply with just one objective and a constraint. So the objective is we want to maximize that value. So each item that we can pick to either put in the backpack or not has a weight and a value. And so we're going to maximize the value of what gets chosen to put into this knapsack. Our constraint, this is the total weight capacity. We cannot exceed that capacity. So our total weight of everything in that backpack must be less than or equal to this capacity or weight limit that we're given. So this is the problem in a nutshell, what we're going to try and look at, and I'll show you how we can work through this from start to finish. So I believe last time I was here, you probably saw a slide very similar to this. And so this is kind of another view of what the quadratic model is. So we need to formulate our objective and our constraints as quadratic expressions. So we can have linear terms like this AIQI, where Q is a variable, or quadratic terms like this Bij times Qi times Qj, where again, the Qs are variables. So basically we are going to define our variables to encode the answer that we want. Does it go in the backpack or not? Those are nice binary variables. And we're going to choose the coefficients that kind of model this problem that we want to solve. And if you're familiar with our quantum computer and everything, you can think about this as we have individual qubits, and then we have couplers that connect pairs of qubits together. So really at the root of this is like the architecture of the quantum computer chip. We have linear terms, individual qubits that we can set a bias on, and we've got quadratic terms, which are pairs of qubits that are linked together that we can influence to either, take the same or take the different opposite values based on these biases that we set. So to build up our model, we're going to write out our objective and constraint in our problem domain. We already did this on that previous slide where I said in words, our objective is maximize value, and our constraint is the total weight is less than or equal to the capacity or the weight limit. So it's really helpful to break this down in like actual words rather than diving right into the math, just to make sure that you have everything clearly split up and exactly in words, kind of compartmentalized. Then in your second step, you're going to decide what are the variables that you want to define. What sort of answer are you looking for? So in this case, I'm looking for which items should I put in my knapsack. So I can think of that as for each item that I can choose, I have a choice of does it go in the knapsack or not? And that's a binary decision. So I'm going to define binary variables, one for each item that I have that choice. And that's going to be my binary variable set. Next, I'm going to take that written word statements of my objective and constraint, and I'm going to convert these now to math statements using those binary variables that I defined. Now, once I've done that, I can dig right into the code and we can encode that very, very easily in our software tools, and we'll see how that works. So let's start diving right in. So here you can see, we defined our binary variables. We're going to have an XI for each item I that we can choose whether or not it goes in the backpack. Our objective is to maximize the value of the selected items. So each item I, we've got a binary variable for it, but we also know the value. That's going to be information we have beforehand. And so here I'm going to maximize the value of the selected items. So I'm going to do for each item I'm going to do the value times the binary variable. And what this does is if an item is selected to go in the knapsack, the binary variable has a value of 1. So we're counting that value. If it's not selected, the binary variable has a value of 0. And so this product is going to be 0 and we won't count that in the value of the knapsack. So just by summing up these terms where it's just a linear term, value times the binary variable, summing that over all of the items I that we can choose whether or not they go in the backpack is going to be the expression that we want to maximize. So here, maximize, this is going to be a summation, and we want to maximize this summation. Next, we have the constraint with this weight capacity. So again, information that we would have beforehand is that capacity as well as the weight of each item. So just like we did on the previous step, we're going to do the weight of the item times whether or not we choose the item. So weight times the binary variable. And this summation is going to tell us the weight of the backpack, the knapsack, for this current solution, this assignment of the binary variables. And we need to make sure that that weight is less than or equal to the capacity. So this is our first constraint. And since that's a pretty simple model with just one constraint, we'll add in another one just to make it a bit more complex. And we'll say that aside from the weight, we can only fit 2 items in the knapsack. So here we're just going to sum up all of the binary variables, and that's going to tell us exactly how many we've chosen for the knapsack and say that's less than or equal to 2. So here's how we went from, the words, those expressions that we had on that word problem. We defined our binary variables, and then we can convert those sentences, the words of our problem, into math expressions. And this can be one of the more challenging parts of formulating your problem. Once you do it a few times, you start to see a lot of patterns and you start to get familiar with it, and it definitely gets a lot easier. But this is probably where people spend the most time is, on formulating their problem, deciding the best way to represent the binary variables, and coming up with these expressions. This was a really simple example, but you could imagine how, a real world scenario would be a lot more complex than this. So now that we have our set of variables, objective, and constraints, we can go right over to the software tools. So our software tools, we have the Ocean SDK, and this allows you to write up a program in Python that you can send over to our quantum computers or our hybrid solvers or whatever tool you want to use to solve it. So for the constrained quadratic model form, we're going to use the constrained quadratic model hybrid solver. So this is an example of the entire program for that problem, right? So I can fit this on one slide. That's how simple and straightforward it is. So just like a normal Python program, you're going to start at the top with some import statements. You're going to import the things that you want to use. We have information going into the problem that you would have beforehand, like the values and the weights of the items. You would have a capacity of your knapsack. And so this is kind of information that you would have on your problem scenario beforehand. So once we have that, I'm just going to count how many different items I have to choose from. In this case, I have 5 items that I need to choose whether or not they go in the backpack. So the first thing I'm going to do is create a binary variable for each of those items. So here I'm making a list of 5 binary variables. So they're just going to be named 0, 1, 2, 3, and 4. And so here I've got a list of those binary variables so that I can access them quickly. Next, I'm going to initialize my CQM, my constrained quadratic model. And so this is just going to initialize it and create a new empty constrained quadratic model. Now, the components of a constrained quadratic model is one objective and a set of constraints. So here I'm going to define and set my objective. So remember that expression for the objective was summing up the value of each item times the binary variable for each item, and we're maximizing that. So here, if you just look at this part, we've got value times binary variable. So that makes sense. And our solvers and our samplers, they all minimize. So this was a maximized problem, maximize value. So the trick there is you just multiply everything by -1, and you've turned your maximization into a minimization. So that's what we did there with that negative. And you can see rather than just the standard Python sum, here I'm using quick sum, which comes from our DIMOD package. If you use the standard sum, it'll work, but it'll be much slower. So we wrote this quick sum function that's a lot more performant, and it'll really speed up your code a lot. You'll notice that it runs a lot faster with quick sum. So I built up just exactly what that math expression said, sum of value times binary variable. And I'm just going to set that as my objective. Now for the 2 constraints, I'm going to do something similar. So for the first one with the capacity, I had the weight times the binary variable. So you can see weight times binary variable less than or equal to W. And I'm going to give it a label that says max weight so I know which constraint that is. So again, using the quick sum, just exactly mirroring that math expression that we saw, sum weights I times xi less than or equal to W. For the next constraint, this was the one that we added where we said we could choose at most 2 items. We're doing the same thing where we're just summing up all of these binary variables and saying the sum is less than or equal to 2 and assigning it a label so I know which one it is. And that's everything that it takes to build up your constrained quadratic model. It's really just define the variables, initialize, set your objective, and set your constraints. And that's it. So once you have those math expressions, you can see how simple it is to work with these binary variables in our software tools. Once you've built up this model and everything, just like what I showed last time I was here, we're going to define a sampler. So I'm going to use the Leap Hybrid CQM sampler. So that's the hybrid solvers. And then I'm going to sample it by sampler.sampleCQM and hand it my CQM. I don't have to provide any other parameters. You can provide a time limit parameter if you want to let it run longer to see if that improves your solutions. But the idea with these hybrid solvers is that they are just ready to go out of the box. You don't need to do any of this parameter tuning that you had to do before with like Lagrange parameters and all sorts of different things. So very easy to use and very easy to get started. So now once I've run this sample, I've stored the solutions in this object called a sample set. All of our solvers return solutions in a sample set object, and they look something like this if you just print them out. And there's a lot of information here, but basically you've got your solutions. So I've got my binary variables 0, 1, 2, 3, and 4. And each row is a solution. So remember the binary variables, it's going to be 0 if I don't choose it, and 1 if I do choose it. So this first row, I can see I'm going to choose item 2 and item 4. And the second row, I'm going to choose item 0 and item 4. And the third solution, I'm just going to choose item 4. So that's how you read off the solutions. Each one has an energy. This is what we're trying to minimize. This is like the value of the objective function that you set in your CQM. You get how many times each solution appeared. And you get also this additional information, which is new. You get, are the constraints satisfied? And you get an array, which I'll show in a second. And then you get a column that says if the solution is feasible. So this first solution that we got back with this lowest energy is actually infeasible. So we're probably going to ignore that one and skip down to the next one, the first feasible solution. So if we translate these solutions in terms of, our items and the weight and like looking at the different constraints. So this first solution, you can see we're choosing 2 items, and the total weight based on those like input arguments that we gave, the total weight for choosing these 2 would be 11. And that's actually over the weight limit that was provided, which is why it's an infeasible solution. The other 2, though, these are feasible solutions. So both of those constraints were inequalities. So it's okay if we choose just one. It was a less than or equal to 2. Now, I mentioned that you might want to ignore the infeasible solutions. So one thing that we've added is a way to filter out those infeasible solutions if that's something that's important to you. So you'll find this in our documentation. You'll see this line specifically in a lot of our code examples, where we take that sample set and we filter on the is feasible column. And this is going to give you a new sample set that includes only the feasible solutions. So it's a nice way to do all of that post-processing for you, and you can just kind of filter out anything that's infeasible. And so to check those constraints, like I mentioned, there was that column that said is satisfied in the sample set. So in that one is infeasible solution, that first solution that came back, if we looked at the entry in that column, you would see false, true, basically telling you that the first constraint, that maximum weight constraint, is not satisfied, it's false, but the second one was satisfied. So you can even go into those infeasible solutions and see exactly why they are infeasible, and that information is all stored in the sample set, again, to make it easier for that post-processing. So as I mentioned, all of these solvers and samplers are available through our Leap Cloud platform. And so what that means is that you can run problems on these solvers, like the example that I just showed you. You could sign up for free, run it right away, and get solutions right away when you run your program. So this cloud service, it's really like real time. So you run a problem and you get answers right away. There's no like batching and waiting and coming back later. The solver runs for like 5 seconds and you get your solutions back, plus like the network latency or whatever it is. But there's no waiting and coming back later. It's very much a real-time cloud service for you to run your problems. So that was a simple example. So I know we went through that quickly, but I hope that kind of made sense, and hopefully with some more time to dig into those examples, you'll really understand how to do this. But what I really want you to grasp was like how easy it was to go from those math expressions to the code. It's very, very simple once you have that formulation to then put it into Python. So let's look at a larger, more complex problem. This is one that's available in our collection of code examples called distributed computing. And we'll just dive right into this example. So when you have a set of computers, maybe like a supercomputer cluster, or a set of different computers that are running a process together, each computer has its own processor, its own memory, but the overall goal of what you're trying to do might have some interdependencies, right? So you might run, one operation on one computer and one operation on another computer, but maybe you need like the output of one to run the other, right? So maybe if I'm running something on here, this computer needs to wait until that's done to send the output over here. So when you run like computer programs or do anything over like a distributed system or like parallel computing, you really want to take into account like how much of these interdependencies there are. You want to try and minimize those to really get performant and good like code and efficient solutions for that distributed system. So how can you minimize that amount of like message passing and waiting? You can minimize that by trying to assign operations to these different processors that are as like independent as possible. So basically assigning operations so that there's as few of these edges as possible. So let's look at an example of this where we model this problem as a graph. So let's say we have these 10 operations that we know need to be completed for this problem that we're trying to solve on the distributed system. So we've got 10 operations and we've got, say, 5 computers, each with its own processor and memory. So I've got these 10 operations, and I know there's some interdependencies on these operations as shown by an edge here. So if there's an edge, it means that like these two have some interdependency. You're going to have to pass a message from one to the other in order to complete the overall goal. So for example, if you were to distribute these 10 operations over those five computers in this way, just by colors, like 1 and 4 would be the operations run on the gray computer, 0 and 2 on the orange computer. If you were to just distribute it like that, then you need to think about like what edges are left, right? So what edges are going between different colors? That's where that slow message passing and like waiting is going to happen. It's really fast if you're on the same processor to get output and continue the operation. But if you have to pass a message, that's going to add some time to your overall running. So these are the messages that would be left that you would have to pass between different computers. So these are the edges that you want to minimize. So basically think about it as a graph where you have a node for each operation, an edge for each of these interdependencies. And we want to partition this network into clusters so that we have as few of these edges between the clusters as possible. And this is what's known as the graph partitioning problem, the graph K partitioning problem, where K is like the number of clusters that you have. So this is a pretty well-known problem in graph theory. It's a very hard problem to do, and it shows up in a lot of different applications. So that's one application with this message passing and distributed systems. Another one might be, looking at social networks and figuring out what types of communities there are based on like activity with, people doing things together, people passing messages together. You can identify like clusters in the graph to identify different like communities in that social network. So there's a lot of different applications. They kind of run all across the board. And so this is a really interesting, hard problem. And so basically we have our nodes in this case are those operations. The edges are those messages that need to be passed. And our goal is to partition it into K sets of nodes. In that example, we had five computers, so 5 sets of nodes. And we want those partitions to be equal size. So we're not going to get any advantage if we put all of the operations on one computer just because we're minimizing message passing. It's not efficient in terms of like the actual workload. So we want to have that distributed evenly with as few edges between them as possible. So what does this look like in terms of a graph? Here's a graph where you might have like 100 nodes. So 100 of those operations and all of those dense interdependencies, all of those messages that need to be passed. And what we're going to do is we're going to take this big problem and we're going to figure out how to make it look like this. So all of the edges in this left picture are in this picture on the right, but we've just now made these clusters so that we have hardly any edges between them. So in this example, we have one edge that goes between clusters. So this would be a really efficient way to partition those operations equally across 4 different computers and really minimize that message passing. So again, I'm going to go through this fairly quickly. This is an example that you can go and look at, and I'll show you in a minute how to do that. But basically the objective, we're trying to minimize those number of edges between the partitions, and our constraints, the partitions are equal sizes, and each node gets assigned to one partition. So each operation is going to be done on exactly one computer. So we're going to use binary variables for this problem. And this is something that you see a lot with problem solving on our solvers, is we're going to have several different binary variables for one partition or for one operation. So for one node in the graph, we're going to have a binary variable for each one of the possible partitions it could be assigned to. And so this is an example of a discrete variable. We're going to define a set of binary variables. And then that's going to make it easier rather than using like integers to like label each partition. It's actually a lot simpler and easier to do it this way. So here we would expect that, you know, exactly one of these would equal 1 for each node in the graph. So our constraints using those binary variables, we want to make sure that the partitions are equal sizes. So if I look at all of the binary variables for one partition, so I'm going to have 1 for each node in the graph, and I sum up all of those, that's going to tell me how many are assigned to that partition P. So I just want that to be equal to, you know, they're all going to be equal sizes. So the total size of the graph, the number of nodes in the graph divided by the number of partitions. So this is a nice equality constraint. And then we also want to make sure that each node is assigned to one partition. So for each node in the graph, we're going to sum up over all of the partitions and say that has to equal 1. So this is your constraint that is making it a discrete variable. And then our objective, this is a little bit trickier. So we need to come up with an objective that's minimizing those numbers of cross edges. So it needs to be a minimization and it needs to be linear and quadratic terms. So let's look at how we can do this. This is similar to something that we did in the last seminar that I gave here when we were making a binary quadratic model. But basically, like if we see an edge like this between 2 orange computers, that's fine. It's on the same computer, right? So there's no cost for message passing if it's on the same computer. So that case is good. But the bad case is when we have different colored endpoints on that edge. When we have an edge and the 2 endpoints are assigned to different partitions, that's our bad case. So how do we come up with an expression for this? Well, we can look at one edge in particular, and we can summarize what are the good cases and what are the bad cases. So if they're the same color, good. If they're different colors, that's bad. And if they're, you know, both the same color, but the color is not orange, that's also good. So in terms of our binary variables, let's look at like one partition. So say like P is the partition that's orange. Then we've got good if they're both orange, bad if one is orange. And if neither is orange, then again, that's fine because that'll be taken care of by one of the other partitions rules. So our system minimizes. So what we want to do is assign a higher value penalty for the bad cases and a lower value for the good cases. And we do that by just replacing these words, good and bad, with larger and smaller numbers. So I'm going to use 0 as good and 1 as bad. And when our system minimizes, it's going to choose 0 and hopefully not choose 1. And so you can literally choose any number you want here. 0 and 1 are just very easy to work with. So that tends to be what I choose. So now if we want to actually go through and come up with a math expression, a quadratic model for this. We can choose, you know, coefficients on here. We can choose like our A's and our B, and there might be some constant C. And so we can choose these so that we get this value column, right? So if I choose A's and B's and I plug in the binary variables for each row, I want it to equal this value column. So here we have 0 and 0. So if I plug in 0, 0, 0, I want these coefficients and this sum to equal 0. So I basically just do out the math, you know, times 0, all of these products are 0, and all we're left with is C. So C equals 0. And so you can just go through and solve this system of equations to figure out exactly what these coefficients are. And this is how we're going to come up with a cost function for our objective. So this is basically how we're coming up with this 1, 1, minus 2. That's what you saw here, 1, 1, minus 2. And so this is for one pair, for one edge. And we need to do this over all edges and all partitions. So you see the same expression, just summed over all partitions, over all edges in the graph. And very important that we just look at the edges in the graph and not, you know, every pair of nodes. If there's no edge, then we don't need to worry about it at all. So that's a little bit more complex of a model to come up with than what we saw in the Knapsack one, but here's a nice summary of it. And so basically our input, we're going to be given this network of nodes and edges and the number of partitions that we want to split this network into. And so we now have our objective. We've got 2 constraints. So now just to, this is the last thing I have, and then we'll open it up for questions. I want to actually show this to you and run it really quick so you can see how you can go back and find this on your own and take a little bit more of a deeper dive on it if you're interested. So let me go out of here. All right, so here I am on my Leap dashboard. So when you sign up for a Leap account, just cloud.dwavesys.com/leap, or from our homepage, dwavesys.com, you can find links to it there. Sign up for a free account. When you first log in, this is what you'll see. And so you'll see how much time you've used, how much of your subscription is remaining. And so when you first sign up, you get a minute of quantum computer time or 20 minutes of hybrid solver time, and they kind of like work together as one subscription quota. So you've got a fair amount of time, you know, 20 minutes of the hybrid solvers. Before I came on, I ran the demo just to make sure everything was good, and it took 5 seconds of that time. So you can really play around with this and, you know, get your feet wet and try it out and see how it all goes. So if I click on this resources tab up here, here's where you can find tons of information on like our documentation. And I'm going to go specifically here to the ocean code examples. And on these code examples, I'm looking for the one called distributed computing. And so if I click on this, it gives you a whole bunch of background on the problem and takes you through a lot of the things that I just explained in the slides. So you can come back and you can take a look at it and see a full explanation of how this is working and how the objective is defined, how the variables are defined, what the constraints are. So you can come back and dive into this when you have a little bit more time. I'm going to load this in our IDE. So when I click this, this is going to open an in-browser IDE, and this is going to install all of the tools required to run this demo just in this IDE in your web browser. So it's not installing anything on your computer or anything like that. You don't have to worry about setting up software tools or your connection to the cloud service. And this is just going to open up and your code should be ready to go right out of the box. So what I have here is a few different files in a file browser. So first there's a README. So just like you might see on GitHub, this is going to give you a full example. If I click this little magnifying glass up here, it's going to give me the nice like preview mode where it looks similar to what we just saw on that last web page. So this is going to have exactly the same description as what you saw on the Ocean Code Examples page in Leap. So you can read through and fully understand the problem while looking at the code side by side. So let's open up the code. That's this demo file. And this demo file is everything you need to run that demo. So it's a little bit more complex than the knapsack one. It's not going to fit on one slide like that one did, but you can see a lot of the same things. So it's setting up the scenario. So building that graph network that we have. It's going to build this quadratic model. And you can see I'm defining my variables, adding constraints, and adding an objective. So very similar to those building blocks that we saw in the knapsack example. Then I'm going to run my problem. So sample the CQM. I'm going to give it a label so that I can see in my problem history which one it is. And I'm going to filter to only look at the feasible solutions. And I'm going to take the best feasible solution. And then I'm going to do some post-processing to make those nice pictures and everything that you saw on the README. So let's just go ahead and run this. And keep in mind, this is going to run live on our hybrid solvers that are in North America. So this is how real time it is. So I am running this in my web browser, just in Chrome. And you can see I built it up. It's now sending it over to the solver. And this is a problem. The graph has 100 nodes, and I'm splitting it into 4 partitions. So that's 400 binary variables, and it's already done. So that's how fast these hybrid solvers work. For a problem of that size, it really only needs like 5 seconds to run, which is really, really fast. So we can look at the input graph. So this is our scenario that we set up. So a big, messy network. There is secretly in there a very nice partition. And so the output graph, it can find that very nice partition there. We've really just got 2 cross edges. And in the code, there's a bunch of different networks that you can run. There's different command line options that you can choose. So you can try something that's doesn't have as nice of a partition, that's more realistic. So lots of different things you could try there. All right. So that is everything I have. And I want to make sure we have time for questions. So we've got about 10 minutes left. So I know I showed you a ton of information, and that was a lot to see, but hopefully it kind of gave you a flavor of what you can do with this newer hybrid solver and where you can go to find more information.
Okay, great. Thank you. Thank you, Victoria. It's an amazing presentation. Very nice. Do we have any questions to Victoria? So actually, I have 2 questions, but I will give a chance to other participants to ask first. I don't see any questions on our chat. So let me maybe ask the first question. So there was information that currently we can use, I think there was information about 1 million variables, or at least 500,000 variables. So
Yeah.
it concerns both binary and integer variables, right?
Yes.
Or, okay, good.
Yeah, the 1 million is if you use our binary quadratic model hybrid solver. For this constrained quadratic model with the binary and integer, the limit is 500,000.
Okay, good. So yeah, I'm super interested whether there are some ongoing development works on just building even more powerful quantum annealers, or these quantum annealing machines, because as you said, currently we have this advantage machine with more than 5,000 qubits. I'm not sure if you can tell us about it, but are there any plans to release or make available even more powerful machine in the next, let's say, 1 or 2 years?
Yeah, so at our Qubits user conference in October, we talked a little bit about our roadmap, and we do have some exciting things coming up. I don't know if it's in the next 1 to 2 years. I think they put on there maybe like, I'd have to look exactly, but I think it was something like 2024-ish for the next Advantage 2 is what we're calling it. And that would be like around 7,000 qubits. And we also announced that we are, at the same time as we're improving our annealer and kind of maintaining that and working forward to get that, you know, as amazing as possible, we're also working on gate models. So we're going to offer both in a few years. So that's really exciting.
Great, great. Yeah, really exciting. So it looks that the technology is getting better and better. And as we can see, we can represent more and more variables, both binary and integer variables. How do you think, when we can expect, or can we assess when we can expect some real quantum advantage, quantum supremacy in terms of this quantum annealing machines comparing to classical computers, or maybe there are already some problems that we can solve more efficiently using these quantum annealing machines comparing to classical computers?
Yeah, so that's a question we get all the time, right? So everyone wants to know that. And one of the things that we've really focused on is what we call commercial advantage. So I think you'll remember like when there were announcements from like NASA and everyone about like quantum supremacy, and then, you know, the next day IBM refuted it. And it's like this very theoretical, very controversial argument. We're really much more focused on the commercial side of things. And so we really focus on meeting our customers where they are and seeing what improvements we can make over their current process. So it might not be like the best you could possibly ever do, but we're interested in seeing like what improvements can we bring to our consumers in their like commercial applications in their business. Like how do we provide business value and improve their current methods? So, you know, we've seen things like retail operations with a customer called Save On Foods. It's like a grocery store where they optimized some of their retail operations, and they took something that used to take them like a week to run, and we got it down to like minutes or something like that. So that's the kind of thing that we're looking at, is like where do we find that commercial advantage?
I understand. I think so. So it is possible that this problem that the company had maybe could be solved more efficiently on classical computers as well, but they but you just compared to the solution that they had at that time, and the speed up was really impressive. So yeah, that's very good. You help the company, and that's good.
Yeah, we have a lot of different customers that are kind of at that point now. We're starting to really see more of that commercial advantage. So it's definitely getting to that like real world size.
Yes. Okay, good. And of course, so beside the time of computations, there is also a cost of computations involved. So that's also something that most likely should be taken into account from this commercial perspective. So I believe that there could be also an advantage at some point. All right. Yeah, that's very interesting. So I believe that we learned a lot about designing programs using these constrained quantum models and binary discrete models as well. Do we have any more questions from our participants? I don't see more questions now. So Victoria, I thank you once again for a great presentation. We are running out of time, but just at the end, I will present a few slides just to announce the next meeting. So it will take maybe 1 minute. Let me share my slides again. I hope you can see my screen. So yeah, we would like to thank once again our strategic partners, Naruto and Kogit, for supporting us, and our honorary partners for also helping us in advertising our meetups. And we would like to invite you to attend our next meetup. It will be on the 13th of May. And it will be this time, it will be the standard time of our meeting, so 6 p.m. Central European time, and our great speaker will be Adam Gloss this time. So we already invite you to join. There will be announcements starting next week. And if you are interested in our activities, our meetings, we also invite you to join our groups, follow our pages, channels, profiles. So let's stay in touch. And that's all for today. So with this, I would like to thank all the participants for attending, and Victoria, thank you once again for this great presentation. So as we agreed, I will share the recording with you, and hopefully we'll later publish it on our YouTube channel.
Great, thank you.
Thank you, thanks. Have a good day, everyone. Thank you. Bye-bye.